you would get the answer, but you're going to take a lot of time to do it, right? You're going to go down a long road for that. So the moral of this little thing is, remember, this is a method that we have on top of what we already have. This is not a replacement for things we've learned. We always want to try and find the path of least resistance, right? And the U sub would be our way to go here. Now, if this was x cubed up here, well then maybe not, maybe it wouldn't go easily with U sub. So, all right. Now, the question is, if you see them, what do you do, right? What do you actually do? Like if you see this, what's the trig sub? Because I don't see any trig here. Did you see trig? There was no trig in those integrals, was there? So why they call this trig sub? What we're going to do in each of these cases is we're going to make a substitution. We are going to replace something in here with something new. And it's going to involve something trigonometric. All right, so let's look at these one at a time. If we get this form, okay, that's the first form, right? If we get this, then what we're going to do is this. We're going to let x be equal to a times sine of theta. Okay, what? If we ever see an integral that involves something like this in it, and we can't do it with basic U sub, we can't figure out any other way to do it, if we see that, what we're going to do is we're going to replace x right here with something more complicated. And that's not a very natural thing to want to do, right? Like x is x. Why would I want to replace it with a sine theta and introduce this trig function? It seems like it's going to get worse, but it doesn't. Okay, let's see what happens. If we do this, right, that right there, that step is our trig sub. We are making this substitution. If we do that, then let's see what this square root would turn into. Right? It would turn into a squared minus, okay, I take the x and square it, right? Well, that's x now. So what happens if you square a sine theta? What do you get? A squared sine squared theta. Everyone see that? That's just me taking that x right there, squaring it, putting it in here. Good? Now you can factor an a squared out of each one. And that leaves you with what? 1 minus sine squared theta, right?
So in order to square the product, you have to square both sides of the product?
To square a product, you square each factor. Right? If I want to square, if there's multiplication, I just square each one.
You square each factor.
Square each factor. Yep. So we factor an a squared out, right? And then 1 minus sine squared theta is cosine squared theta by the Pythagorean identity. And so now I have square root of a squared times cosine squared theta. And now I have a product, right, between these. Does everyone follow? That becomes that, just Pythagorean. Do y'all see I have a product now? And so I can take the square root of each one. And if I do that, I get a, right? And then I just get cosine theta. So if I make this substitution, what's going to happen is this complicated square root thing is going to turn into just an a cosine theta. Now I will have switched the variables, right? I started at x and now I'm at theta. So I will eventually have to get my answer back to x. But my integral is going to involve cosine, and after what we've learned in the first part of this section, I'm feeling pretty good about those types of integrals, right? In theory.
So why are we able to say x is equal to a sine theta?
Because we're in control, right? I mean, we can always make a substitution. We can always say, let something be something. It's one of the rare times in math where you have the control here. Like you can do it, right? We do this because we can, but also because if we do it, if the original form looked like this, do y'all see that every time we do it, that's the result, right? Yes.
How would we know that it's going to be sine? Is it always
How it's?
sine?
Oh yeah. If you see this form, that's what you're going to do.
So it's always.
Always.
Okay.
Yep. If you see this, that's what you do. This right here is the trig sub.
Oh,
This is the trig sub step that I'm here to teach you or show you, okay? Someone showed me, I show you, all right? So this is the trigonometric substitution step. We see that, we do this every time, yes?
This looks very similar to the antiderivative of the inverse sign? Is that?
The antiderivative, yeah, okay. It is. We can prove it. We'll prove it, all right? We'll make that our first example, all right? All right, y'all ready to do an example with this? Okay, let's do that then. We'll start with our first example. Your first example, integral 1 over the square root of 1 minus x squared dx. We want to know the antiderivative of that, right? Andy just brought up the fact that you recognize that that's the derivative of inverse sine, right? We should know, is that a question?
Yeah, I was going to ask, can you know where you took the square root of that denominator?
Square root?
Or sorry, like, in other words, like, can you just say that the denominator is 1 minus x?
No.
Okay.
So I think what you're asking is like, can you square the bottom and just get rid of the root?
Yeah.
No?
Yeah, more or less.
Oh, I know what you're doing. Oh, no, you can't do that.
It's like 1 squared minus x.
I think I know what you're doing. I think what you're doing is you're trying to tell me that that's the same as this. And trying to do the square root of each one individual. Is that what you're trying to do?
I see the problem.
You see the problem? Okay.
You
Can't do that. Again, wouldn't algebra be a lot easier if you could? Right? If algebra worked the way our brains want it to work, right? It would. But then it wouldn't work. Like our system wouldn't work. Our system is very precise.
Are those 3 cases on the?
I'm getting to it. I'm getting to it, yeah. Let's just try and understand what I'm doing here first, all right? So do we all understand that our answer should be inverse sine x? Because we know that the derivative of that is that because I showed you that before. But let's do it using what we just learned. So we look at that, first thing I do is I look at, can I do basic u sub? I see that, I don't see its derivative, right? The derivative of the inside here is 2x, negative 2x, I don't see it anywhere. So u sub's not going to work. Integration by parts, good luck, it's not happening, all right? You're not going to be able to come up with a table where anything's going to work, all right? Trig integrals, sine, cosine, secant, tangent. Well, there's no sine, cosine, no secant, tangent, right? So the only thing really left for me right now is the trig sub. And it should be already glaring that I have a square root of 1 minus x squared there, right? That should be glaring at me. So I have this right here, which means that I'm going to do trig sub. And I want to remember that in this case, a is what? A is 1, right? A is 1 in this problem. This number right here is a squared. So a is 1. Also, what's the substitution I'm going to make? I'm going to let x be what? A sine theta, so that's 1 times sine theta, right? Which is just sine theta. So all I'm going to do is replace x with 1 times sine theta. And I'm not even going to do the integral right now. I'm just going to work out what this is, okay? So let's keep going. That means that the square root of 1 minus x squared would become the square root of 1 minus what? 1 times sine squared theta, so just sine squared theta. You'll see there's nothing to factor out. That's just cosine squared theta underneath the root. And that's just cosine theta. Yes?
Well, I got to that point, it turns out to be the integral of secant x.
Almost. You're on the right track. There's one more thing we have to keep track of here. There's one small but critical step, right? So right now, as it sits, we are going to replace that expression with that, right? So let me show you where that is. That is going to go and replace this. And now what's in blue here is going to have theta in it, right? But what's out here? Dx. We need that to be d theta. Where are we going to get that from? Well, we're going to take our original trigonometric substitution. This substitution right here. This is our relationship right here between x and theta, right? We are saying that x equals sine theta. That was our trig sub, right? If this is an equation, I can differentiate both sides. So I'm going to take the derivative on the left, dx, right? with respect to theta is equal to the derivative of that, which is cosine theta, right? Just take derivative on both sides. And can you solve that for dx? Yes. It's what? Dx is cosine theta d theta. Right? Just multiply both sides by d theta. I feel like I lost people here. You're okay?
We'll catch up.
This right here is that, right? And now I can rewrite the whole integral.
Is that because you're treating it like it's an implicit differentiation for x?
Yeah, I'm differentiating both sides of this equation with respect to any variable I want. I chose to go with respect to theta because I'm trying to figure out how to make that a d theta. So I need a d theta over here somewhere. So I do it with respect to theta.
So you need a d theta because you made the denominator theta.
This is going to have thetas in it, right? So my integral needs to have a d theta.
Because you can't have two different.
That's right. You need the same variable. Yes.
Do you always differentiate both sides of an equation?
With respect to anything you want. Exactly. Is that what you're asking me?
Yeah.
If you have an equation, you can always differentiate both sides.
Can you integrate both sides?
Yes. It's just a question of what are you differentiating with respect to and what are you integrating with respect to. So what are you treating as your variable,
Right.
right?
And you could just make up a variable in anything.
That's right. I could have differentiated this equation on both sides with respect to time. And then that would be a related rate problem back in Cal 1, right? We always took equations in Cal 1 and we differentiated them with respect to time because we wanted to find the relationship, how the rates of change were related to one another with respect to time changing. Related rates, right? So you can always differentiate with respect to any variable, even if it's not a variable that appears here. So I could differentiate this with respect to m.
And it
I
would
could.
just be
dm equals sine, oh sorry, I'm going to do it. If I took this and I differentiated both sides with respect to m, which is a variable that's not even here, then I would get dx dm equals cosine theta times d theta dm. That's what it would be.
because you've chosen m to be the.
I've chosen m to be some variable.
So like if you had, I'm not trying to take it off track, but so if you had like a, b, c,
Mhm.
you wanted to pick one of those to differentiate from, then the others would just be dA, dB, and then whatever.
Yeah. Mm-hmm. Yep. All right. Can we get back here? I'm going to rewrite the integral now. This integral now becomes 1 over cosine theta right here, right? Cosine theta times the dx, which was cosine theta d theta, wasn't it? And the cosine thetas cancel out, which just leaves us with the integral of 1 d theta. And what's the antiderivative of 1 with respect to theta is theta, not x, right? So this is theta plus a constant, right? Because I did the antiderivative. So our answer is theta. That's a problem because our original problem was in terms of x. So I need to get back to x now. So I go back to, again, where do I have a relationship between theta and x? Right here, right? I would like to solve that equation for theta, right? So I put it up here. X is equal to sine theta. I would like to know what theta is, so I take inverse sine on both sides of the equation. And of course you get theta over here, right? And you get sine inverse x here, and then that gets replaced, and you have the answer we thought we were going to get, right? How important is that dx in this problem? Yeah, I mean, if you don't have that dx getting replaced with that cosine theta d theta, then that cosine never cancels, and it's not going to work, right? So this is our first problem, okay? This is our first just introduction to this. I'm going to do a new one. Do you have a question?
Yeah.
Yeah.
How did you, the last step, getting it back to x? I don't know.
Okay, so do you remember this was my trig sub, right? This was the big substitution I made, right? This is a relationship between x and theta, isn't it? So I took that equation and I wrote it down again up here. And then I said, I'm trying to find out what theta is. To get that theta out of the sine, I took inverse sine on both sides to kill off the sine on the right and make theta. And then over here, you see it?
Yeah.
This is a critical piece of our problem. This right here, this substitution is going to be used throughout the problem. Let's do another one, because this one, the flow of this one is not the way I normally do these problems. I want to start a problem from scratch. Now that you kind of have an idea of where I'm going, you'll see how I set things up, all right? Let's do one where A is not 1. Let's do one where A is not 1, and let's do one where we know the answer. We don't know what the answer is, okay? Like that one we knew the answer, right? See, if I can do one problem with the remaining time, I'll be good. I guess we'll do this one. Yeah, let's do this one. Now, I will say that this may be able to be done a different way. This problem, there may be another way to do this one. But let's just do the trig sub so you can just see it happen, all right? All right, so we look at it, we go, you know what? I see the square root of a squared minus x squared, right? I see the square root of a squared minus x squared. So I'm going to do a trig sub because I know that this kind of looks like this. And for us, the a is what? 4. A is 4, right? I'm just kind of identifying things right now. So that's the start. I realize I've got this form. See it right there where A for me is 4. Okay. Normally I don't write that step down, but I'm doing it because it's the beginning. Here's what I usually do. All right. So this is going to be the beginning of what my work usually looks like. I start with that and I say x is equal to 4 sine theta. That's my trig sub. That's me letting x replace, I'm going to replace the x with 4 and then sine theta. Why do we use sine theta? We always use sine theta when we see this form. Yes? No. That's a different trig sub. There's 3 different forms and there's 3 different trig subs, and I'm only showing you one today. Okay? Now, next thing I'm going to do is take the derivative of it. Now, I know you're like, why? It's because I know I need the dx, don't I, at some point? I'm just going to do it now. What's the derivative of this? Well, if I differentiate the left side with respect to theta, I get just dx d theta. Over here, I get 4 cosine theta, and then I'll get that d theta. Right? Because that d theta would come out over here. It would be dx d theta, and then I move the d theta to the other side. So are we good with that? Yeah? Where did I get it? Well, do you see that that's a 4 if it follows this format? 4? Anytime you ever see this, the substitution you will make is this. Every single time. If you see this, you're going to replace x with this, a sine theta. Got it? Yes?
So once we know that trig sub, like, we don't have to write out the steps like every single time we do that. You just can tell by looking at it.
What steps are you talking about?
Like to replace the x with a.
Yeah, like all this. You don't need to write all that.
Yeah.
Just go right to this.
Okay.
Now, this next step, this is going to be dependent on you. Like for me, I know, because I've done enough of these problems, I know that if I do a sine theta, if I do that trig sub, I know what this whole root's going to turn out to be. It's going to turn out to be what? 4 cosine theta. Because I've been through the algebra of that. We did it generically, didn't we? When I first started this idea, I said, look, if you do this, and you replace the x with a sine theta. We worked it all out, and we got a cosine theta at the end, right?
Yeah.
So you're either going to do that yourself by hand or get to the point where you can just write that down right now. This is this.
Oh, okay.
If you take this x and replace it with that and go through all the work, right, factor out something, blah, 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 you'll get this. These are my 3 pieces of information that I'm going to need to continue the problem now.
So once you find the derivative, you can just, or actually, so once you find the derivative more or less without the d of theta.
Nope, this is not always this.
Okay.
Yeah, now here, in this particular trig sub it is, but in the others it's not, so I don't want to start saying whatever happens there, just, no.
So, but it doesn't give us the derivative of it. It just lets us know that that can equal sine. Right.
That's, yeah, this, all I'm doing is setting up all the pieces I need to be able to attack the integral now. I know that everywhere I see an x, right, everywhere I see an x, I'm going to replace it with this. Wherever I see dx, I'm going to replace it with this. And anywhere I see this square root, it's going to turn into this, right? That's what I'm going to do. Now, I didn't show that step, but look, I'm going to do it real quick. If I replace the x with this, I square both of those, I get 16 sine squared theta, right? I factor out a 16, 1 minus sine squared theta. 1 minus sine squared theta is cosine squared theta. Square root of each one, 4 cosine theta. That would happen every single time I do it. So I get to the point where I don't do that anymore. I just go straight from here to here. You might have to do this if you haven't memorized it. All right, ready? Time to go after the problem now. It's time to actually try and do this integral. So, I don't know what we're going to do, actually. Yeah, I'm just going to see what happens. So I do integral, right? And now, what's x cubed? Well, x cubed is that cubed, which is that cubed, right? So I cubed the 4. 4 cubed is 64. Okay, and then I cubed the sine. Sine cubed theta. All right, everybody? That is that, right? Okay, what about the square root of 16 minus x squared? What's that? 4 cosine theta, right? That's this. So this times 4 cosine theta, that's this part. And finally, do not forget it, the dx. What's dx? 4 cosine theta d theta. Yeah, constants are about to come out because they're just a pain in the ass to have. There. Everyone see where all those pieces came from? Do you see that we now have a trig integral? And that's what the first part of this section was about, right? So I'm going to do this, man, that's a big number. 64 times 4 times 4, what is that? 1024? It's definitely a power 2. That sounds right. 1024. Integral sine cubed theta cosine squared theta d theta. Good? How do we handle sine and cosines together when the power on sine is odd and the power on cosine is even? Well, let's see. Let's see. How do we handle that? Way up here. Shit, where is it? Okay. We had sine is odd. We had sine odd, right? We have cosine odd. We have sine odd. So with sine odd, I'm going to use a Pythagorean identity. I'm going to pull out one factor of sine. Now, I knew to do that, but I wanted to show you, like, that's what I think you would be doing at this point, right? Going back and looking. Yes?
I'm sorry, I'm
64 times 4 times 4. Someone told me 1024. Is that right?
Yeah, that's right.
Okay, yeah.
Wait, so, and then, so that's like a foil then, right?
It's up what?
Like a foil? Like a
Foiling what?
The constants. You can take the constants out of the integral.
Yes.
Okay.
But it's not FOIL. FOIL is like when you're multiplying binomials together and you, right?
I always consider
The operation between all of these is multiplication, right? So all we're doing is multiplying, right? Everything in between these is multiplication. So we're just moving things around.
Oh, yeah, because it's not 64 sine cubed. It's 64 times sine cubed.
That's right, times. Yep. I need to leave that up there. So I'm going to come right here. Let's see. I'm only going to have 7 minutes. Let's see what happens. I'm going to go equals 1024 integral. All right, I'm peeling off a sine. So it becomes sine squared cosine squared theta times sine theta. There's the sine I peeled off. And because I peeled that sine off, I know that this is the derivative of cosine, right? Well, I'm off by a constant. But that means that I need all of this in here to be cosines. Now again, this says this on your little table chart thing, your little cheat sheet, but I'm just telling you the way I look at it. I know that's derivative of cosine, so I'm going to make a u sub here. 1024 integral. I need to get this turned into cosine, so I turn it into 1 minus cosine squared theta. Don't mess up and put x now, because we don't have x's anymore. Cosine squared theta times sine theta d theta. That's where I am. And then my u sub, right? Not trig sub. I'm going to make a u sub now. My u sub is cosine theta. And the derivative of that is negative sine theta d theta, which I see right here is the derivative. But I'm off by a sign, right? So I have to scale it and make that a negative du. Y'all there? All right, we keep moving this train down the tracks. All right, where am I now? 1024 integral. I'm ready to make my substitution. Everywhere I see cosine goes a u. So 1 minus u squared times u squared times what? Negative du, right? So how about I just make a slight tweak here. Instead of writing negative du, is it all right if I put that negative out here on the 1024 and then just slap a du here? What now? Distribute the u squared through, and then we're going to use power rule, right? Okay, so I've got this. Negative 1024 integral of u squared minus u to the fourth du. Power rule, I can handle that, right? Equals negative 1024 parenthesis 1/3 u cubed minus 1/5 u to the fifth. All of that plus some constant that I don't know. And then replace u with cosine theta. And then you got to get that back. So hold on, we're not done. Integral, I'm done with the integral. 1/3 cosine cubed theta minus 1/5 cosine to the fifth theta plus c. Right?
Well, we would have got the right answer if we just wrote to the first plus c, right?
No, you're not done. Because right now, this answer right here with plus c is not done because your answer is in terms of u. So that's like me asking you your favorite color and you tell me like you're 10. You know what I mean? It's like they're not the same thing, right?
That exists.
All right, so we need to get back to x, right? How do we get back to x?
Do you differentiate with respect to x or something?
Nope, nope. What was the key thing that connects x and theta together for us? This right here. That right there. Always go back to the original substitution you made because that connects the two things together, right? And now what we're going to do is something we did like the first or second day of class, and that's we're going to create a reference triangle. Okay, so from this, right, remember all I need to figure out is what's cosine theta right now, okay? So what I'm going to do here is I'm going to take this, I'm going to divide both sides by 4 and create that expression, right? Just divide both sides by 4. And then I'm going to draw a reference triangle. It's a right triangle, and this right triangle is going to be a visual representation of that equation. So I'm going to put theta here as my angle. Sine, by definition, is which side over which side? Opposite over hypotenuse. So if I label this x and that 4, do you agree that this picture represents that equation? Yeah. Yes? And we don't want to know what sine of theta is, we want to know what cosine of theta is. Off of this triangle, to get cosine, you need the adjacent side. But I know 2 of the 3 sides, so I can find that side, right? Just using Pythagorean. So I'm just going to call this A for adjacent. Well, I better not call it A. We were using A earlier. Let me call it B. Okay, B. So I know that b squared plus x squared must equal 4 squared, which means that b squared plus x squared equals 16, but that means b squared equals 16 minus x squared, but that means b is the square root of 16 minus x squared. So I'm just solving for b. Using Pythagorean, solve for b. Yes, is that a question?
Point that out that that's actually at the beginning of the integral.
Yeah.
That's the beginning of the what?
At the integral.
We had that this was equal to, what are you saying? It's part of the original. This is the thing that the trig sub came from, right? Is that what you're saying? Or are you saying further down? If you look further down, do you remember when we wrote it? We actually wrote it down, right? Right? Remember we wrote that down? There were 3 things I put check marks on. This was the 3rd thing, right? Do y'all see that we could have just divided both sides by 4 here and we would have had the same thing happen? Okay, can't do that all the time though. Sometimes this won't be cosine. Like sometimes we're looking for like something like tangent over there, so you need everything. So the reference triangle is the way to go. I'm almost out of time. Let me see if I can't just at least give you a final answer here. So I have equals negative 1024. No, negative 1024, and then I have 1/3. Okay, what is cosine theta? This side, which is that, over 4, right? So if I put that in here, it's square root of 16 minus x squared over 4, but all of that cubed, right? That is cosine theta cubed. Cosine theta cubed. Minus 1/5, and then cosine theta